So many people here on Zoom. A lot of family, also Kensuke, and um, some past mentors. Yeah, and past friends or friends, obviously.
I think we might as well start. So welcome everyone. It's fantastic to have Miela here to give her PhD defense. This is the public part of the PhD process, and you're going to hear about the work that she's done over the last 5-ish years in the department. So just a little background. Miela came to us from UC Berkeley, the other what would we call it? The East and West Coast. There's a lot in common between Cambridge and Berkeley. Anyway, you came to us with a degree in physics and then joined the ECS department, but maybe that was too big of a jump from physics to engineering. So she settled in the middle, which is materials science and engineering. So we do both science and engineering. And you'll hear about a project which involves the science of domain wall motion and the science of these fascinating oxide materials, as well as engineering to make devices which will potentially be useful for logic and memory. So along the way, Miela's done a huge amount of other stuff which will not show up in this, but I want to particularly give you a shout out for your community service. So Miela's always been one of the people in the group who's so generous with her time, not just within the group, keeping our equipment running, training people, helping everyone who asks, but also in the department, in the ECS being a member of, what is it, the Graduate Women's, and then the GAP program, which helps seniors apply to college. And just so many different examples of helping out other people through the community as well as on the scientific side. So let me hand over to you and thank you.
Awesome. Thank you, Caroline, for that kind introduction. And thank you all so much for coming live and on Zoom. I really appreciate it. And I'm really excited to talk to you all about what I've been working on the past 5 years. The title of my defense is called Domain Wall-Based Magnonics in Iron Garnet. And hopefully y'all will understand what that means by the end of this talk. So if I can get my laser pointer to work, it might have just died. Okay, might be doing this manually. So, okay, a little bit of just the outline of what my talk is going to be. And I'll just keep coming back to this slide to just showcase our progression throughout the next 45 minutes. So why are we interested in magnetics for computing? And that starts out with Moore's law, which states the computer processing speed doubles every 18 months. And the way the semiconductor industry has been able to maintain that is with this little diagram on the right, by basically shrinking hardware. But hardware can only get so small until you start to run into effects like electron tunneling, joule heating, all inherent to conducting electrons. So that's where magnets come into play. Magnets are non-volatile, fast-switching, tunable, and provide a more compact memory storage option for the semiconductor industry. And the fields of spintronics and magnonics aim to do just that in developing magnetic-based logic and memory devices compatible with CMOS technology. Oh, it's working. Awesome. So what are the advantages of magnetic-based computing? So magnets like to hold a magnetic state. We can use that to store information. And there's a variety of mechanisms, including spin transfer torque, spin orbit torque, spin Hall effect, magnons that can effectively read and write into these devices. In addition, spintronic and magnonic devices have the potential to be very energy efficient. And a lot of that energy efficiency comes from their non-volatility, which is inherent to magnets, meaning that you can store information without needing a power. And lastly, PMA stands for perpendicular magnetic anisotropy. That's basically when you have a thin film magnet, the preferred axis that the magnetization likes to lie upon is in the out of plane direction. And that offers low energy barrier switching and short domain wall widths, advantageous for downscaling devices. So spintronics and magnonics, they aren't just all theory. There are a few examples of magnetic-based computing in the world today, including giant magnetoresistance sensors, and they're used in ABS systems, usually mounted onto the axle of cars, to detect variations in wheel rotation speeds. Also, magnetoresistive read heads read data from hard disk drives. Hard disk drives are in a lot of modern day computers. They're high density memory storage things. And then STT-MRAM stands for spin transfer torque magnetic random access memory. It's a magnetic counterpart to traditional RAM that's known for its low power consumption due to the non-volatility of magnets. So why am I telling you all about this? And that brings me to my work, which my work aims to contribute to the fields of magnonics and spintronics, and that I study magnetic materials and their magnetization dynamics for device type applications. More specifically, have it in bold here, I study the interaction of spin waves and domain walls in iron garnet. So iron garnet is our magnetic material, and spin waves and domain walls are two magnetic phenomena, and I study their interaction in iron garnet. So let's talk about each of these three key ingredients. Firstly, spin waves. Spin waves are collective excitations of magnetic moments in a material. Magnons are the quantized unit of spin waves, so I'll say magnons and spin waves pretty interchangeably throughout this talk. You can think of them as magnetic energy. The amplitude, frequency, and phase of spin waves can be altered similar to electronic signals, which is a great way of processing information. And spin waves propagate through a magnetic material and interact with magnetic textures like domain walls or skyrmions without moving electrons. So it provides a promising platform for low energy devices. Okay, our next ingredient here are domain walls. Domain walls are the region where the magnetization changes between two domains, showcased here in this little picture, and then here in this little diagram below. Domain wall propagation is how domains switch or magnetization or move, and they're induced through mechanisms like spin Hall effect or magnons, for example. The speed of this domain wall propagation is inherent to a material's Gilbert damping constant. So, for example, bismuth substituted yttrium iron garnet, which I'll mention later on, has reported domain wall velocities that can reach 4 kilometers per second. The last key ingredient here is iron garnets. So I'm sure you all are familiar with the January birthstone garnet. And while the elements here are a little bit different, the structure of the crystal is the same. They're actually really complex crystals. They have 160 atoms in a unit cell, which is a lot. But despite their complexity, we could break them down into 3 different sublattices. So I'm going to change the chemical formula up in the right-hand corner to look at the site occupancy in each sublattice. So I go through this. So the dodecahedral site is the largest. It's also called the C site. It has the biggest atoms, which is rare earths, yttrium, bismuth, even calcium in some cases. Then the next site is this A site here. It's an octahedral site. It's where some of the ions sit. And the last site is the D site or tetrahedral site, which is where some other ions sit. And each of these sites have their own magnetic moment. And the way that those magnetic moments sum up deems this material ferrimagnetic. And that means both ferromagnetic and anti-ferromagnetic properties can be probed. For example, garnets have pretty low Gilbert damping, like I mentioned in the bismuth yig and some other types of garnets, which allows for fast magnetization dynamics, but they still have a net magnetic moment like this that allows us to read out their magnetization. This net moment can be tuned to lie along a specific orientation, and that's called magnetic anisotropy. Growth, magnetoelastic, magnetocrystalline, and shape anisotropy all contribute to the net magnetic anisotropy of iron garnets. It allows us to achieve things like the PMA, perpendicular magnetic anisotropy, in thin film garnets, and that can be probed in both epitaxial and non-epitaxial film growth. So like single crystal and polycrystal and stuff. Yeah, and that comes from a combination of strain and ion substitution, specifically in the magnetoelastic anisotropy. And that ion substitution happens in this rare earth site here. But this ion substitution also allows us to tune other magnetic properties, including saturation magnetization, coercivity, compensation temperature as well. And lastly, these garnets are insulating, which means there's no conducting electrons to worry about energy loss or thermal effects. So this slide here shows all the different properties that you can tune by basically putting different rare earths in those C sites of iron garnets. And so you see on the plot on the right that the magnetization as a function of temperature really varies drastically depending on what rare earth you have in those C sites, or yttrium, for example. And some of those rare earths have this thing called a compensation temperature. And a compensation temperature is basically a temperature that garnet has a net moment of 0 because all of those sublattices magnetization cancel each other out. And that's really interesting for probing antiferromagnetic properties in these garnets at that specific temperature. So how do we grow iron garnet thin films? In this lab, we grow them through pulse laser deposition, otherwise known as Ph.D. And pulse laser deposition is a great method of growing complex oxides because it allows us to tune a lot of different parameters in the film growth. So firstly, we can reach a base pressure of less than 10 to the minus 5 torr for our growths, and that mitigates impurities. Also, we have a substrate heater above our substrates, which allows us to heat the substrates to 400 to 650 C during our garnet growth. That adds extra kinetics to aid in the crystallization of the garnet structure. And we also are able to flow in oxygen while we grow these garnets around 10 to 150 millitorr. And that actually helps us maintain chemical equilibrium pressure as we're depositing the garnet. Lastly, it wouldn't be called pulse laser deposition without a laser. So we use a krypton fluoride excimer laser, which has a wavelength of 248 nanometers. And it's focused to a fluence of 2 joules per centimeter square at the target surface. And I added a little video of garnet live to show you all what this process looks like. Okay, so my thesis goals. My goal here is to show you how I study the different properties of garnet, magnons, and domain walls in developing a right mechanism for a domain wall-based magnonic device. Firstly, I dive into studying iron garnets, specifically developing a model to look at the magnetization as a function of temperature for garnets based off their stoichiometry. I then study the interaction between magnons and domain walls in iron garnet, showing domain wall spin wave induced domain wall motion. And lastly, I use that to demonstrate bidirectional domain wall motion in that domain wall based device. So now I'm going to dive into my little simulation. So we developed this model because predicting the moment of ferrimagnets as a function of temperature becomes very challenging, as each of the sublattices causes the overall net moment to vary non-monotomically. So previously in 1970, this guy Dion developed a molecular field coefficient approach, but his systems were limited to near perfect bulk materials. And in the 70s, that's what you were working with. But here we look at thin film epitaxial growths where off stoichiometries could be stabilized. So here we designed a Python model in Dion to predict the magnetization of iron garnets with a large variety of compositions and defects. So this slide is the only theory slide, so please bear with me. I'll try to move through it quickly, but it's how our model works. So as I mentioned previously, the net magnetic moment of our garnet is a combination of the moments of each sublattice here. And I added a picture in the upper right-hand corner to remind you all what each of those sublattices are and their site occupancy. Each sublattice can be broken down into their 0 temperature magnetic moment and a Brillouin function, If you don't remember what that is, I have it listed here. It takes in this input X here that has a temperature dependence, as well as the properties of whatever magnetic ion you have. And then this molecular field coefficient here describes the inter and intra sublattice coupling between that site and itself or neighboring sites. So I have listed here a ton of different rare earths and other ions that you can substitute in those C sites, their magnetic properties, and these molecular field coefficients. And the negative values in the coefficients correspond to parallel coupling, and the positive values correspond to anti-parallel coupling. So to showcase the accuracy, to showcase the accuracy of this model, I basically modeled a ton of different rare earth iron garnets as a function of temperature, and then also their angular momentum as a function of temperature. And to showcase the accuracy of this, I overlaid a little snippet from Dionne's magnetic oxides book to show the accuracy. And you can see it fits pretty well. So this model can do more than just that, though. It can also account for multi-rare earth iron garnets. So here I have gadolinium substituted yttrium iron garnet, or YIG, and for various amounts of gadolinium substitution. And then I have gadolinium substituted dysprosium YIG. And you can see that this compensation temperature, or the antiferromagnetic state, varies as a function of your rare earth substitution. And I modeled that a little more clearly on the right here. Looking at dysprosium substituted gadolinium iron garnet, we see compensation temperature of the magnetization and an angular momentum compensation temperature diverge as your amount of dysprosium substitution increases. So this might be useful for a researcher who wants to model dysprosium gadolinium iron garnet with a TA near room temperature, for example. So that model would tell you, okay, you want to have gadolinium 2, dysprosium 1 iron garnet to get that kind of composition. And you can see that this model will not only plot the net magnetic moment as a function of temperature, but also what each sublattice does to help the researcher visualize. And then on top of that, it'll plot the same thing, but for angular momentum as well. So now I said that I could expand this model to the bulk stoichiometries of epitaxial films. So this is an example of how we do that. So terbium iron garnet was grown by a colleague, Ethan Rosenberg, and grown to be extremely terbium rich. He was able to stabilize this non-bulk composition by epitaxial growth. And he found from TEM elemental mapping that the terbium to iron ratio was 0.86. And what we'd expect in bulk is only 0.6, so it's super terbium rich. He also found from XMCD data that there was very little iron 2+, but the iron octahedral to tetrahedral, or A site to D site ratio, is 0.63, which again is off from what you'd expect in a bulk composition. He modeled this, he experimentally took data of the MS versus temperature curves of these samples, so we could use our molecular field model to understand what the A, D, and C site occupancy were here, because we have a few more unknowns than knowns. So we first look at the Curie temperature, which was different from what you'd expect from a bulk material, and we're able to determine that there was no additional iron vacancies in the A site, which then from experimental data we're able to determine that there was about 16%, 0.47 vacancies in the D site, which meant there was about 24% terbium in the A sites. And that excess terbium had molecular field coefficients itself that we had to fit based off this magnetization versus temperature data. It resulted in these plots, and as well as the site occupancy that gives a really good fit to both the overall magnetic moment as well as the compensation temperature and the Curie temperature of this off-stoichiometric film. In addition, we also looked at calcium substituted YIG of bulk samples. This calcium substituted YIG is really interesting because it's actually a little conductive. But we wanted to understand what was going on with the magnetic moment, because calcium's not magnetic, but nor is yttrium. Calcium would be substituted into the yttrium sites because of its large ionic radius, but why would that change the net magnetization? you can see on these M versus T curves, and I'm going to just highlight this red and, red and black curves up top, that the low temperature MS is a bit lower, and the Curie temperature over here is also a bit decreased. So we had a hypothesis that calcium likes to be in its 2+ state, and again, it occupies the C site with yttrium, but that's then that leaves us with a bit of an off charge balance. So then there would be some iron 4+, probably in the D sites, the balanced charge. So we look to our model to model what would the resultant M versus T curves look. And we see, we see from our MS curves that there is a slight decrease in the MS from just pure Yag to the calcium substituted Yag, and also a slight decrease in the Curie temperature. We modeled that a little more closely, looking at increasing substitution of calcium in the C sites and iron 4+ in the D sites, and saw that lo and behold, the change in Curie temperature from experimental data matches what the model says, and same with the low temperature change in MS. So that was great because it also confirmed that not only do we have calcium 2+ in the C sites, but that introduces the presence of iron 4+ in these D sites. So in summary, we've shown that our model Dione recursively calculates that magnetization and angular momentum of various iron garnets with a lot of defects in off stoichiometries. And when we can use this model to fit experimental data like the terbium-rich terbium iron garnet and the calcium Yag, it allowed us to determine more precisely the site occupancy of those samples. And I wanted this model to be available for not just me. So I put it on GitHub and it's available open source at the following link here. So now I'm going to be moving into the spin wave and domain wall interactions. I'm studying spin wave induced domain wall motion in iron garnet. So spin waves have been shown to translate angular momentum with domain walls as a method to move them. And this has been shown previously in cobalt nickel multilayer films. However, the high Gilbert damping of these magnetic conductors limits domain wall velocities to only 10 meters per second. As I mentioned, in some of our garnets, we can have really high domain wall velocities because of that low Gilbert damping. So here we showed spin wave induced domain wall motion in bismuth substituted Yag, which requires as little as a few picojoules of energy to propagate domain walls up to 15 microns. So I mentioned that there's an exchange in angular momentum here. So I want to break that down before I get into the results. So I'm going to blow up our little animation here. And basically it's just showing a bismuth Yag racetrack across, and then these two RF antennas we patterned on the sides, and a spin wave that's been excited from, for example, when we send it an RF pulse through the left antenna, it'll excite a spin wave radiating down the bismuth Yag track. Going to remove the antennas for clarity here. So as the spin wave as the spin wave propagates down this bismuth Yag track, it's going to eventually run into a domain wall, and the two magnetizations are going to be opposite on either side of the domain wall. So we'll have an upstate here and a downstate here, for example. In order to keep the spin wave progressing down the bismuth Yag track through the domain wall, there's going to be a difference in angular momentum between the two sides, and that energy has to be conserved just because of laws of energy conservation, and that energy will then be put into the domain wall to propagate it to the left. So that's the breakdown of what we're trying to model here. So let's get into the results. So first we grew 17 nanometer thick bismuth Yag on a garnet substrate with pulse laser deposition. You can see the thin film characteristics in these plots here. The takeaway is the out-of-plane zero field FMR frequency is about 3.5 gigahertz. That's the frequencies we're going to be sending into those RF antennas. The hysteresis curve here that just taken in the out-of-plane direction shows PMA, that perpendicular magnetic anisotropy. And then we patterned our devices on this film, and that involved etching down those little bismuth Yag racetracks, and that was done via ion milling. And then we patterned copper and gold antennas via E-beam evaporation. So after that, we wanted to look at the spin wave transmission between two antennas to see if we could even excite spin waves. So we sent in an FMR signal between the two antennas on a bismuth racetrack with it all magnetized in one direction. And between 3 and 5 gigahertz, you see a peak around 4.1 gigahertz that shows, okay, something's going on. We're exciting some magnons. We then wanted to repeat this experiment with the presence of a domain wall between those two antennas, and we still see that same resonance peak around 4.1 gigahertz. However, it's significantly attenuated, which tells us that there's some sort of energy exchange between the spin waves and the domain wall that we had that was between the two antennas. So this brings us to the setup of our spin wave induced domain wall motion experiment. And I have our little animation in the corner to remind you guys what we're looking at. And you can kind of compare. This is our bismuth racetrack. These are RF antennas. And this image was taken with MOC. So it's a MOC image. MOC stands for magneto-optical Kerr effect. And what that does is it basically allows us to visualize the magnetization and very magneto-optically active materials like this bismuth gig. So for example, that's how we can see that this bismuth racetrack is nucleated in the upstate here, and then the downstate is in the dark region on the right here. The region between the up and the down states, these little areas here, are where the domain walls are present. So for our experiments, we're looking at stuff around the antennas, which is why I blew this up over here on the right. So what we do is we send in an RF signal through one of our antennas here. It excites spin waves radiating away from the injector antenna until it reaches a domain wall here. Once it reaches the domain wall, that exchange in energy will propagate, the domain wall to the right towards the injector source. So it's going to move in the opposite direction of the spin waves. Okay, so let's actually get into some results. So here I show a couple different MOC stills, of progressive domain wall motion. So we start with a domain wall nucleated under this antenna up top, and the injector antenna is down below here, indicated by the little lightning bolt. We've noticed that our antennas also create little localized strains in our bismuth racetrack, which is basically changes that anisotropy in that region and creates a pinning site for those domain walls. So we see them often nucleating under the antennas. After a RF pulse of 1 millisecond, around 4.1 gigahertz, which is near resonance for this bismuth device, we see the domain wall move a couple microns towards the injector source. A sequential RF pulse at a slightly increased power moves it another micron, and then a third pulse, again another increased power, moves it the remaining 7 microns towards the injector antenna. We repeat these experiments, but with off resonance RF pulses, and we don't see any domain wall motion. So now I put these little MOC images together in a movie, or I like to call them motion pictures. And basically, in this MOC movie, we see a domain wall, which is nucleated under this antenna on the left. And then our injector antenna on the right here is sending in an RF pulse of just 1 nanosecond in width and 4.35 gigahertz in frequency. That is resonance for this particular device. And after a 1 nanosecond pulse, I'm going to keep playing that movie. We see that the domain wall moves an entire 15 microns between these two antennas under the injector antenna, which is pretty awesome. And that, when we consider the power loss from the RF pulse to spin wave excitation and then the decay length of the spin waves, we calculate the RF pulse or the actual energy of the spin waves to just be 4 picojoules, propagating the domain wall 15 microns. So I want to look at some statistical switching behavior. And this is on that same device, which is shown here. And that's that 1 nanosecond pulse corresponding to this little data point here. We wanted to look at how the carrier frequency of the RF pulses and the pulse width of those pulses changed the minimum power threshold needed to switch or move the domain wall in these devices. So We can see in the plot on the left that a 1 nanosecond pulse, the only frequency that actually moves the domain wall is its resonance for this pulse, which is 3.5 gigahertz or 4.35 gigahertz, excuse me. As our pulse width widens, we see the range of carrier frequencies that can induce domain wall motion also increase. However, there's always still a dip or like a minima around around the resonance of our device. If we move to the right here, we see increasing pulse width decreases the power threshold needed to move the domain wall. However, there's two specific regimes here that this trend is following. And on the left, we see a constant energy. And then after about a microsecond pulse and larger, we see this stochastic depinning regime corresponds to creep or like room temperature thermal effects affecting the domain wall depinning. So the way that I fit these two trends, like these two regimes, with the equations here on the right. Constant energy is not groundbreaking, it's just power times time. So power of the pulse times the pulse width. And then the stochastic depinning regime uses an Arrhenius law, excuse me, and that involves the power switching threshold switching power, an inverse attempt frequency, and a zero field energy barrier. We were able to fit this equation to the data on the right, and that gives a zero field energy barrier of about 0.62 electron volts. So in summary, we have demonstrated spin wave induced domain wall motion in our PMA bismuth-Yig, showing that the spin waves translate the domain wall, towards the spin wave source. Around FMR frequency, we see the power of the RF pulse is most effectively coupled to the antenna, from the antenna to the spin waves, yielding the largest effects on the domain wall. And then at zero field, we see the domain wall move 15 microns from a 1 nanosecond pulse, which again translates to just those 4 picojoules of spin wave energy. But I have more questions that I'd like to explore in this project, and that involves investigating the effects of both magnons and also small magnetic fields on the domain wall depinning in motion, and then seeing if we could use this information to demonstrate some back and forth domain wall motion. And that brings me to part 4, developing a domain wall based magnetic device. So like I said, I want to study this a little more closely, and that actually begins with characterizing the magnons excited in the bismuth-Yig racetracks to understand what are the spin waves we're working with here. And then I'd like to explore effects of magnons and external fields on the domain wall depinning in motion, and use that information to demonstrate this back and forth motion. So I grew bismuth-Yig again. 19 and 20 nanometers of bismuth-Yig was grown on Garnet substrates. We see very similar behavior, like characteristic or characterization compared to the past films. The only difference here is we see a little bit lower PMA. That doesn't change anything other than like those resonance frequencies that we're exciting, that we're using to excite the spin waves. And then I did some upgrades to our little MOOC setup, which allows us to find that the coercivity increases once the racetracks are etched. And so that's what these little pictures are showing here, or MOOC images is what they are. So at -8 millitesla on the bare film, the film is nearly saturated into the down state. However, if we apply -12 millitesla to the same film just after it was etched, only half of these little bow ties, these are our little racetracks, have flipped. So that's important for when we apply those small fields to our experiments. So we used the characterizations in the past slide, and my colleague Andrea was able to simulate the dispersion relation of the bismuth-Yig racetracks and find a zero field FMR frequency of around 1.5 gigahertz. And he also was able to take the dimensions of our antennas that we patterned here on the right and see how they're like what kind of magnons we can excite based on superimposing this excitation efficiency onto the dispersion relation. What we found is that these antennas most efficiently excite low mode spin waves of a K around 1 radian per micron, which have a group velocity of 30 millimeters per second. And that's what this simulation looks like. So we have some low mode spin waves. However, we want to see more progressive domain wall motion. So it's actually advantageous for our purposes here. So now we're looking at spin wave transmission, again, more characterizing the magnons and the spin waves in our bismuth-zinc devices. We were able to show spin wave transmission between two antennas up to 70 microns apart. So that's like pretty far apart for a magnetic material. And we're able to use that information to back out the Gilbert damping constant of our bismuth YIG, which was 3 × 10⁻⁴. And that's a very low value, and low damping corresponds to fast domain wall motion and very long decay lengths of our spin waves, which allows us to explore long range spin wave domain wall interactions in these devices. So I'd like to go back to, or not go back, but now show you all some more motion pictures of the domain wall motion in these new devices. And you'll notice we have these little half bars pinned here, or patterned here. And these half bars are used, again, to create that little localized strain, to change the anisotropy locally in those regions and provide pinning sites. And basically, what that allows us to see is the sequential pinning sites of the domain wall to observe progressive domain wall motion. And that's exactly what this movie shows here, is the domain wall slowly inching towards the injector antenna. So we see it'll just be pinned a few, like about 4 microns away from the antenna initially, and slowly start to move all the way under that injector antenna. And I said that I could see more long-range interactions, so that's what this slide shows, which is domain wall motion from spin waves it shows domain wall motion in devices spaced 20 here, 30 here, and 40 microns apart. And these are all spin waves excited from 100 nanosecond RF pulses near the resonance of each film, and that's labeled in each movie. And we add some small external fields too, and what those external fields do is we hypothesize they both lower the depinning energy of the domain wall, as well as increase the spin wave speed as well to aid in that domain wall motion. Yeah. So now we want to look a little bit more at the statistics of what's going on here. And these plots are pretty similar to what you saw earlier, but instead of just looking at carrier frequency and pulse width versus power, we also add the effects of these small external fields on our device. And these fields, I wanted to mention earlier, are all below the coercivity, like well below the coercivity of our devices. But the plot on the left shows, again, we see a power threshold minimized around the FMR frequency of our device here, which was 1.5 gigahertz. But as we increase the external field applied to our device, we also see a shift in that FMR resonance frequency that corresponds to how the carrier frequency of the pulse most efficiently excites spin waves. Then if we move to the plot on the right, we see how pulse width again shows this constant energy versus stochastic pinning regimes. And they intersect similar to our past project around 100 nanoseconds. As we apply external fields, the depinning barrier lowers the power threshold, or excuse me, their external fields lower the power threshold needed to depin these domain walls. However, we don't really see a change in these regimes from the external fields. So now this is the fun part. This is the part that I'm very excited about, which was looking at the directionality of our domain wall motion. And the way we set up this experiment was to have competing effects between spin waves and external fields. So we start with this initial state here, and there's a down state, as you can see, around this injector antenna, And that means we have this little domain wall about 4 microns to the right of this injector antenna. As I've shown in the past, spin waves like to propagate domain walls towards the injector source. So the spin waves are going to encourage the domain wall to go under the injector antenna. However, if we apply small negative magnetic fields, it's going to encourage the expansion of this downstate, which is going to propel the domain wall to the right, so away from the injector antenna. So as we first start off, we don't apply any external field, and we see, lo and behold, the spin waves completely pull that domain wall under the injector antenna. But as we start to apply negative magnetic fields, you start to see this competing effect. The spin waves wanting to pull the domain wall left, and the negative magnetic field wanting to push the domain wall to the right. And that causes the domain wall to get pinned just a little bit outside that injector antenna. As we increase the negative fields, that domain wall gets pinned a little bit further and further to the right, until finally we're back at our initial state here when there's no domain wall motion. And that we're gonna like call an effective field of our spin waves, because we have equal and opposite competing effects of the spin waves trying to move the domain wall to the left and the negative fields trying to push the domain wall to the right. And if we keep increasing that negative field, we see the domain wall actually start to move towards the right because it's dominating this regime here. So I did that for a couple different pulse conditions, and and this is the resultant plot of what we found for just 10 nanosecond pulses. But I wanted to change the pulse width and also the pulse power to show how that effective field and how those competing effects also might change. And so with the longer pulse widths here, you see a steeper change in the domain wall direction. However, with increasing powers, we actually didn't see any changes. But across the board, you see a consistent effective field of about 0.8 millitesla from the spin waves. The only outlier here is this guy, which is the 1 microsecond pulse width, and that has a smaller effective field of 0.5 millitesla. And it's the one condition that was in the creep regime versus the constant energy regime. So it might have some other thermal effects going on there. So I would love to use the knowledge that I gained with the past couple slides to try to create this back and forth motion. So that's what this slide is all about. It's showing back and forth motion of these domain walls with small external fields and very short spin wave pulses. And so this, I thought, is a great model for writing type mechanism with just, again, these really small magnons and small external fields, or excuse me, not short RF pulses and small external fields. So the pulse conditions for the movies you see on the right here are listed here. Specifically, we used 1 microsecond pulse widths with these devices. However, if you remember previously, I was able to show domain wall motion of domain walls moving 15 microns with just 4 picojoules of spin wave energy. And if we were to look at like modern CMOS transistors that are on the size of like tens of nanometers, they use about 10 to 100 femtojoules for write energies. If we were to downscale this effect to like similar size, we would be using 4 femtojoules of energy instead of just 4 picojoules. So still pretty significantly low energy kind of mechanism. Now you all might be asking, what's the application of this? Where could you even see this going? And there's a lot of demands to meet like higher density memory storage, that semiconductors have started to look to alternatives to just traditional electric memory. And one of those alternatives is racetrack memories, which basically use the position and motion of domain walls to store information in these tiny thin strips of magnetic material. And they've been proposed with mechanisms like spin orbit torque and spin transfer torque. However, both of those mechanisms involve electric currents, which raises concerns for joule heating and energy efficiency, which is inherent to just electrons moving. Spin wave induced domain wall motion, however, offers a promising energy efficient method to locally write magnetic bits without the concerns of thermal overload, because you don't really have anything moving. Spin wave propagation, and again, these really small external fields below the coercivity of your film can control the locally written domain state. And spin waves propagate domain walls irrespective of their type, we found, and that expands the range of magnetic materials and textures that can be effectively manipulated in this kind of racetrack memory. Lastly, spin waves can be excited with various means. I've shown the use of RF antennas, but also localized strain, laser pulses, spin Hall effect are all other methods of integrating this kind of um, technology into racetrack memories. So, in summary, I have continued to progress my work with characterizing magnons in the bismuth-Yig racetrack, measuring damping to be 3 times 10 to the -4, which is very low. We showed the combined effects of small external fields and spin waves on domain wall motion and deep pinning. And then we demonstrated back and forth domain wall motion with just these tiny external fields and microsecond RF pulses. Finally, I get to wrap things up. So in summary, I have developed Dion, which recursively calculates the magnetization of various iron garnets with non-bulk stoichiometries. I've demonstrated and characterized spin wave-induced domain wall motion and iron garnet, and used that knowledge to showcase back and forth domain wall motion, which is magnons and small external fields. And there's a lot of different directions you could take this work moving forward. So if I was here at MIT for a couple more years, I would probably want to expand on the spin wave domain wall stuff and explore alternate methods to excite spin waves, also study the effect of annealing on garnet films and substrates. We've shown that really has a strong effect on domain wall pinning sites. Also, growing polycrystalline bismuth-Yig on silicon and then fabbing that into devices, I think would be really interesting to try to do. It would bring the work also one step closer to CMOS integration. And then also just downscaling these devices to study this effect on the nanometer scale, and maybe even try to get this back and forth motion with just magnons and no external fields. And lastly, during my time here at MIT, I contributed to a lot of other projects. I couldn't talk about all of them here, so I wanted to just list some of them, and then some other ones we still need to write up. So yeah, now I get to go to the fun part, which is acknowledgements. So firstly, thank you so much to my research community, specifically my thesis committee, Caroline, Professor Liu, Professor Baldo. Thank you so much for your time to read my very, very long thesis and be here for my talk and advise me through this process. Caroline, you're an outstanding advisor, and I love being able to talk about magnets and cats with you, and your excitement for the field is just contagious. Also, I have some other mentors in this community. David Bono and Charlie Settons have really helped me a ton through this time here at MIT, just helping me with equipment setup and also just understanding what I'm doing in these different experiments too. They're just irreplaceable sources of knowledge. And then my mentors from before MIT, Dr. Dula Parkinson is actually my first mentor in the science research community. I started my research endeavors at the ALS at Berkeley, at the micro-CT beamline. So if you want to talk to me about microwavable Cheetos, I could tell you about that too. Dr. Don Boucher gave me my first internship at the Aerospace Corporation, which is actually where I found spintronics. And that propelled me to join Professor Saif Salahuddin's lab at Berkeley. And they really helped me make it to MIT and prep me for grad school. And then this row of people here has really helped me at my time at MIT. Nick and Andrea, and then Carlos from a couple summers ago, you all have spent endless hours with these domain wall experiments, and I really appreciate your work. Jackson was my first mentor here and just a wealth of knowledge and definitely why I'm still organized. Oops. And then Henske and Takian have been also a great wealth of knowledge, and I've learned a ton from both of them. Jason was actually my first grad student mentor back at Berkeley and was helped me learn the field of spintronics. And even sometimes I would message him here from MIT, like, how do we get this sputter system back working? And then Yabin, his knowledge in the field has just been incredible. He was the one who first had this idea of the spin wave induced domain wall motion in Garnet, and he's been a great mentor through my time here. And also to all these guys in this bottom row, I could not have done what I've done without their help. Brian is why I understand LabVIEW, which is amazing. Mark is how I've done all my EBL patterning on Garnet, which is very difficult. And Dennis was a photolithography expert. Gary, the E-beam evaporation expert. Lars, Katie, Sarah. These have all kept me from burning down building 13. Just been great. Leslie and Janet have helped me in the administrative office in the EECS community, and Damien has been a great leader in the USEM community as well. And then I'd also like to just thank like the broader spintronics community, specifically my lab group and my collaborators. They've been a great group to work with. We've gone on some fun trips like kayaking, escape rooms, helping David, and it's a great time. And then my friends, thank you all so much for just making this time here at MIT so worthwhile. We had a couple weddings during my past 5 years here, not myself, but I did take people wine tasting to Napa. And then I'm also a huge tea person, so we went out for tea to lots of ski trips, lots of over-the-top birthday parties from myself, and paintballing extravaganzas where me and my friend Katie tried to dress up as endangered species. It did not work. Yeah, just it's been a blast. And then the horse community. So if any of y'all know me personally, horses are a huge aspect of my life. As you can tell from this picture, I've been riding since a very young age, thanks to my mom and grandma. And I have an emotional support horse, Zoe, I like to call her, who I have taught over the past 14 years to tolerate my hugs. And she actually ended up retiring in about a couple years ago. But this barn here is Holly Hill. These 3 ladies, it's actually many of them, it's just hard to get them all together in one group, have really been a huge source of my like stress relief from my time here in school. Maybe a source of some of my stress in the horse shows. But I've been able to do some really cool things when I've been able to escape lab. And these are actually all pictures of me riding from the past 5 years. So I really like horses, if you can't tell, and they're really a good source of my like de-stressing and just engagement with nature, which has been really nice. So I really thank all of everybody from my riding community for keeping me sane. And then I'd also like to show you all a few pictures of my family. We're Irish Catholic, which I think should explain enough. We're a part of the population problem, and we have a lot of family outings. These are also actually only photos from the past 5 years. And we get together a lot. They will all be coming to my commencement, so brace yourself. But they're fabulous. And then I also like to thank my parents. As you could tell, I was not the easiest kid to raise. I had a lot of meltdowns, as you could tell, or a lot of temper tantrums. I had pink hair throughout all of my elementary school years, and also many broken bones. But no, my parents have been great throughout this whole time. They especially have really taught me the importance, or the insignificance, I should say, of gender roles. Like they really helped me pursue physics, not thinking twice about being a female in the field, and now engineering. And just by saying like, who cares? Like embrace your femininity, but do whatever you want. And I think that's been super incremental to my success here. So I also have a brother, if you guys didn't know. So I included some photos of my brother too. And during my time here at MIT, my mom also graduated school back in 2020. I almost pointed to my graduation. Back in 2022, she got her bachelor's and is now graduating with her master's this spring. So I'm really excited to celebrate that as well. And she can therapize everybody now because she's going to be a therapist. And lastly, there are mistakes in lab, and I would like to kind of normalize some of those mistakes by showcasing everybody a couple examples of things that have happened just by equipment getting old. And you all know I've managed quite a few different systems, so I've seen a lot of things. And then this is me spinning around in the clean room because I can. So stripped bolts and nuts were not that unusual here. My poor parents have watched me strip so many screws, and I think it came back to haunt me here by having to sometimes saw some of them off with Dremels. And so yeah, that's one thing. One day I managed the sputter system in our group, and one day we were like, why does the sputter gun keep losing plasma? It's just shorting. And we opened up the chamber and it's just a few flakes of metal shorting it. Wasn't terrible. Nothing broke actually, so that was good. I also learned the limits of the RF power cables. Great. And I also learned how to fix them. I did a lot of patterning during my time here at MIT and how I took little pictures of a camera so they're blurry, but how it should turn out versus how it often turns out are two very different things. And we struggled with a laser that was dying in our Ph.D. lab before we got a new laser, and it was getting super divergent. And so we kept having to realign the optics, and I was like the optics aligner person. And it was getting to the point where the mounts of our mirrors were bleaching out from our laser, which was kind of funny. But now it's better because it's new. And I've learned a few things about bearings during my time here because they're bearings that hold the target carousels in pulse laser deposition systems. And I've learned that if one starts to go, all of them start to go. And once we had this fun visit from facilities that we didn't know about, and they shut off the chiller connected to our sputter gun or sputter system, and we didn't know, and we melted an entire target. That was luckily it's just aluminum, so it's fine. But yeah. And then one of my like biggest Cambridge fails was I had a procedure done on the back of my right ear, and I found out about the attempted Trump assassination, and I had that procedure done that Monday after. I don't care what your political preference is. Walking around in Cambridge looking with that bandage on my ear for a week, Cambridge is not a very welcoming community to MAGA supporters. It was not fun. And then this wouldn't be a complete presentation without me showing some of my writing mistakes too. So I know not a lot of you have a lot of horse knowledge, but you shouldn't have that much distance between the horse and the saddle and the air of the fence. So I'll play this movie where I basically messed up and this poor little mare saved me. But we kept going, and that's really what matters, is just learning from your mistakes and keeping going. So yeah, so mare named Sally, who is great. And then lastly, for Caroline, this little video of my cat Scribbles playing with the balloon strings I got for my mom when she graduated. Yeah, that's it. Thank you all so much. I'll just
You all see that doing a PhD is a lot more than just being in the lab. Right? And it's a miracle you actually got as much as you did done in the lab, considering all the time you were doing other stuff. So even more. Congratulations. Okay, so at this point we have questions from the audience. So who wants to go first?
Thank you.
I just have a very simple question. The domain laws do a switch to them durability or last long.
Oh, do they have durability or last long? It's technically not even like a particle. It's just like the change in the magnetization. So the actual properties of the domain wall are inherent to your magnetic material that you're studying. So with
Like if you turn off the switch,
it just stays where it is.
it-
Mhm.
oh, that's the problem.
Yeah, that's again like dependent on your material properties. So depending on however your magnetic material is engineered, if it has if it'll
That's another
yeah, exactly. Thank you. Yeah, Alex.
About like miniaturization, but like how small can you scale down like single diagram exhibition for like
Yeah.
a bit of memories?
Yeah, no, that's actually a great question. So the magnons themselves, they have a frequency like a um spin pro or wave vector properties, just like phonons, for example. So it's going to be particular to your magnetic material. That's why like antiferromagnets are pretty advantageous because you can excite really short or high energy magnons in your material and downscale it pretty well. You also really have to worry about your domain wall widths too. And that again is another magnetic material property. We did a simulation and found the domain wall widths in our bismuth yake are about 40 nanometers wide. Yeah. Yeah.
So
real.
like in an actual like memory, let's say you want
Mhm.
right? You were saying that like you need to the frequency at which it takes to change from one
Excite,
thing,
yeah,
like depends on the exact like structure.
exactly.
So is there a way to like, is the idea like, would you want to make the frequencies of all these different things the same? Like,
Yeah, I think, I mean, it would be easier to make it all the same
Yeah.
and then you only have to worry about one frequency. But yeah, the benefit of this interaction is you're doing it in ferrimagnets, so you really don't have a lot of stray fields to worry about because the net moment's pretty small. And there's no conducting electrons. So the whole like thermal, like Joule heating concerns or thermal dissipation, like not really a problem here. So you wouldn't for what it, at least like what I would suspect if you were to make this into like multiple devices close together, you don't really have to worry about engineering them to have different excitation or different resonance frequencies.
so from like a manufacturing perspective, you would try and get.
You would try to just have it all the same. At least that's what I would assume. Yeah, for
Like
sure.
where would these excitation pulses come from? Like
Yeah. Oh, like how we would
in a
excite
real device, like
in a real device. Yeah. So you could do the RF antennas, but then you have to worry about some sort of conduction. You also can actually modulate strain, and that can excite domain wall, or excuse me, not domain wall, spin waves. So people will put these like magnetic materials on top of piezoelectric substrates and modulate the strain a lot, and you can excite spin waves that way. You also can do like really high frequency laser pulses like femto or yeah, I think it's femtosecond pulses, I think, can excite spin waves as well in your little magnetic material. Because they use already, there's this like technology, the uh laser induced hard drive, nah, I'm forgetting the name, but the hard disk drives that use like a little laser to switch the bits a little bit easier. So like there's already lasers involved in traditional CMOS technology. So another thought. Yeah.
I don't come from a science background, so this is very general, it seems. But for a device that uses conductive material versus magnetic material, what would be like proportionally the power savings?
Yeah, so this material, I was saying, like, if we were to downscale, like the 4 picojoules of spin waves moving the domain wall 15 microns, like bits in like traditional CMOS transistors are like in the tens of nanometers, and they use like femtojoule level, so like 10 to 100 femtojoules. If we were to scale down our process to those same dimensions, it would be about an order of magnitude lower of energy. If everything goes perfectly.
Questions? Oh, well, let's thank Miela again. Our audience leave and we'll let the committee ask Miela some more questions. If you guys want to hang around outside, you can.
Okay.
Um,
Thank you all for watching.
guarantee how long it was.
Okay, I'm gonna stop the Zoom and then talk to you all. Okay, I'm gonna end the Zoom meeting.